for my background. Okay, let me just start. Okay, we should
Hi
start.
Daniel, there is some sidebar. Is it possible to get rid of that?
Uh, okay, let me try. Oh, okay, it
Yes,
works.
thank you.
Yeah, thank you. Also, okay, let us start with the Dirac's theorem. Um, Dirac's theorem goes back to 1952, and it says that in any two connected invertex graphs, we have a simple cycle of lengths at least 2 multiplied by its minimum degree, or Hamiltonian cycle if this number is too large. So by delta here, I always mean the minimum degree of the graph. And this theorem doesn't say nothing about graphs having cycles of length more than that. But we can, from this theorem, take a polynomial algorithm to find such a cycle. And unfortunately, this bound is tight, even for k-connected graphs, for greater connectivity numbers. And if we try to find a cycle of greater length, we obtain that the relative problem is NP-hard. The proof is pretty simple by reduction from Hamiltonian path or cycle. Yeah, please ask the question.
So for k-connected graphs, you mean it will be k times delta g, the cycle length, or it is 2 times delta g?
No, it is even 2 times delta g. So even if we increase the connectivity restriction in the statement of the theorem, we won't get any better bounds.
Of course.
Um,
Thank you. Yeah, it will decrease.
okay, at least for path, we wouldn't get better bound, but I believe that this bound is tight even for greater numbers. I'm sorry for now. I'm not really sure, but it should be tight. Yeah. Okay, and the friend of this theorem is the theorem of Erdős and Galai, 7 years later. It says that if we want to find a path between two given vertices, say S and T, and the graph is two connected, then we can always find the ST path of length at least delta, at least minimum degree. Okay, so this is the starting point of our research. Can we do better than that? Can we find paths or cycles greater than these bounds? And we see that if we try to improve multiplicative factor, we obtain that the cycle is NP-hard. And even if we add some function that has low dependency on delta, it is also NP-hard. Okay, and some other point that we can start from is a work by Janssen, Kozma, and Nederlof, presented at WG 19. Its title is Hamiltonicity below Dirac's conditions, and they prove that they can solve Hamiltonicity, so decide whether the graph is Hamiltonian, when the condition of Dirac's theorem, let me go back to the previous slide. So we see if delta here is at least n/2, we obtain a Hamiltonian graph. So Janssen, Kozma, and Nederlof, they studied the question, what if this condition is almost satisfied? So first, the first problem they consider if we have at least n minus parameter vertices of degree at least n/2. And the second problem they study if this degree of all vertices in the graph is at most n/2, so n2 minus k, minus small number. And they prove that they have single exponential FPT algorithms for these problems, for both these problems. And important conjecture they pose. What if we have simultaneously first version and the second version. So we have restriction only on n minus k vertices, and this restriction is also relaxed. So we have degree at least n over 2 minus k. They conjecture that this problem is also FPT single exponential. Yeah, so this is some other starting point of our research, but to actually formulate a problem that would generalize the Dirac's theorem and this notion, we would like to state another version of Dirac's theorem. And this can be called Dirac's theorem with bad vertices. It's just a generalization of the standard Dirac theorem. So if here we take some subset of vertices in the graph and we delete it from the graph, but the initial graph is to connect it, we would obtain a simple cycle in the initial graph of length at least 2 delta of minimum degree of the graph where these vertices are removed. Okay, so this theorem can easily be proved. I won't get into the details. It allows us to capture the conjecture because we can take these k vertices that have a small degree and put them in the set B, in the bad vertices. And then we would get that delta is at least n popolam n over 2 minus 2k. Okay. So let us formulate the problems that we consider. The problems are, the first problem is long Dirac cycle. It is the center problem of our work. So we're given just a graph and the set inside it and the parameter k. And we want to find a cycle that would be longer than our generalization of Dirac's theorem provides. Yeah, so we would like to increase the number of guaranteed cycle, increase its length by at least k. And the friend of this problem, I'm sorry, so this problem is good for the reason that it captures the equation of Janssen, Kazma, and Nederlof. And I should note that this is always a S instance when k is equal to 0. And the friend of this problem is a longer Dirichlet ST path. So it is formulated in the same way. So the guarantee theorem holds even for the ST path. Yeah, and we would like to find a path of length more than that, more than guarantee. Yeah. Any questions so far? You can ask question anytime you want. I can see if there is a question in chat or by raising a hand. Okay, so our main result is that we proved that both these problems are FPT and algorithm for them are single exponential, depending on k. Okay. So to provide some intuition, let us consider a very simple example. So assume you have a graph and you want to find not a cycle, but a path of length at least to delta plus 1. We now consider that the set of bad vertices is empty, and this will be for most of the work, for most of my talk, because bad vertices are just some technical thing, and for most topics that I discuss in this talk, bad vertices are irrelevant. Okay, so we would like to characterize graphs that have no path of length to delta plus 1. Okay, so we start with a cycle of length to delta. Its existence is guaranteed by the theorem. Of course, we have to connect the graph. And then what can we have outside this cycle? Okay, assume we have an edge outside this cycle. Then because the graph is too connected, this edge should be connected to the cycle. And as you can see, we immediately obtain a path of length to delta plus 1 just by taking this edge and following the cycle. Okay, so if a graph doesn't have a path of length to delta plus 1, all vertices should be isolated outside the cycle. So the cycle is a vertex cover of the graph. Okay, so we have some isolated vertex outside it. Otherwise, everything is trivial because we have a Hamiltonian cycle. Assume that it has two neighbors on cycle that are adjacent on the cycle, that are neighbors on the cycle. Then we can increase the length of the cycle like this. And we, of course, if we have another vertex, we would obtain a longer path. So we increase the length of the cycle. It is now to delta plus 1. And then we just take one isolated vertex and append it to the cycle and obtain a path of length to delta plus 1. Yeah. So if the graph doesn't have a cycle above guarantee, it should look like this. So each vertex outside the cycle cannot have adjacent neighbors on the cycle. So it has exactly half of the vertices. So it should be like this. Okay. So assume that we have another isolated vertex such that its parity do not coincide with the parity of this vertex. So we have its neighbors as non-neighbors of this vertex. So we have such isolated vertex. Then we also can increase the length of the cycle. And the length of this cycle would be to delta plus 2, and we immediately obtain a path of length to delta plus 1. Okay, so we know that any vertex outside the cycle should have the same neighbors on the cycle. So all vertices have the same neighborhood, all isolated vertices. Now I will prove that non-neighbors of isolated vertices cannot be adjacent. So assume there is an edge between some pair of such vertices. Then I will show you that I can construct longer cycle following this edge. It looks like this. So we just use this edge and use that we can use any neighbor of a non-neighbor on the cycle. And then we again obtain a cycle of length at least to delta plus 1, and this gives us a longer path. So we know that vertices of this type are independent. They are called 101 neighbors because its neighbor on a cycle is a neighbor of isolated vertices from one side and from the other. So it's 101. So vertex cover is exactly these vertices. So the vertex cover of the graph is of size exactly delta. But we have a simple bound on the length of the longest path in the graph. Upper bound. This upper bound is 2 times the size of vertex cover because each edge should be incident to a vertex inside the vertex cover. And we just proved the theorem that a 2-connected graph G has no path of length to delta plus 1 if and only if its vertex cover size is equal to its minimum degree, or it has no enough vertices to that. Okay. Any questions so far with this simple example? So we showed how to solve the problem for path if we have k equal to 1 and no bad vertices. I think it is some step, and yeah, indeed it is some step because ideas of 101 neighbors would be used in the following statements. Okay, and an interesting fact is that this doesn't hold for cycles, because for cycles we can have this picture. So as you can see, this graph is of minimum degree exactly delta, but you won't find here any cycle longer than 2 delta, because you need to follow these two vertices, and from these vertices you can go only inside the clique, and in clique you can have only delta minus 1 vertices, so you can obtain at most 2 delta. Okay, so for cycles, this theorem do not hold. And this is some insight on the structure we will have in the following slides. Okay, so if there are no questions, let me go to the next slide. Okay, and in fact, paths are easier to find than cycles because you can just add a universal vertex. So the lemma is very simple. If you have a connected graph and the longest path in it is of length p, then if you add a universal vertex, you obtain a two-connected graph that has a cycle of length p plus 2. And we obtain that solving long Dirac paths on two connected graphs. I'm sorry, path and cycle are interchanged here. So solving long Dirac cycle on two connected graphs, we solve long Dirac path for connected graphs automatically. So you can see that if we have a graph, here we have a longer cycle, and if we add a universal vertex, we just have a cycle of length plus 2. Yeah, and we can, in the other direction, we just remove the universal vertex from the cycle and obtain the path of the length cycle minus 2. Okay, so we focus just on finding cycles, not finding paths. Good. Okay. And the main result that was presented in literature that we rely on, that gives us many insights on the structure of the graph, is the proof of lock of Dirac's theorem. In fact, I wasn't able to find this proof in some paper of lock, but you can find this proof as a sketch in pure HTML, just like it. So on Lock's personal site, you can find this proof if you try to Google it. Okay, so I will go through this proof. This proof actually allows us to prove the Dirac's theorem, but we use its ideas and we modify its ideas to provide us with some other structure that happens if we have short cycles, if we cannot find very long cycles. So, okay, assume here that we have found some cycle of length to delta plus p. And of course, we assume that p is really small compared to delta, because if p is some significant part of delta, we can just use color coding and obtain a single exponential equity algorithm. So p is smaller than some fraction of delta. Okay, and we again look at what lies outside the cycle. It can be an isolated vertex. It can be an edge. It can be a separable graph. By separable, I mean a graph containing a cut vertex. And it can be a two-connected graph. Yeah, so these are components that occur in the graph when we remove the vertices of the cycle. Okay, and I will show you first that if we have an edge outside the cycle, then we can immediately increase the length of the cycle. Okay, so we focus on the edge. Okay, so assume first that we have neighbors like this, and they are consecutive on the cycle. Then, of course, we can simply increase the length of the cycle like this. Okay, assume that we have neighbors that are on a distance 2. Then we also can increase the length of the cycle, because we remove from it one vertex and add 2 endpoints of the edge. Okay, so denote the endpoints by u and v. And then if we have a neighbor of u and a neighbor of v on the cycle, we have that the distance, the arc of cycle between them, should be of length at least 3. Okay, now we will do some arithmetic. Okay, let S be the set of common neighbors of u and v on the cycle, and T be the set of all neighbors of u and v on the cycle. We know that the length of the cycle, I denoted by C, should be at least 2 multiplied by the number of neighbors of u and v. Because if you have consecutive neighbors, you can increase the length of the cycle. So, okay, each arc between the vertices in T should have length at least 2. Yeah, as you can see on the picture. You cannot have these, okay, or you can have this picture also. You cannot have the neighbors adjacent on the cycle. And also, we can add S to this bound, because if you have an arc which endpoint is a common endpoint of u and v, then this arc should be of length at least 3, because you can follow the edge. Yeah. So here the picture, you see that the common neighbor of u and v, it is to the right, and to the left you see just a neighbor of u. And this is arc of length 2, so you can increase the length of the cycle. So this arc should be of length 3 if you would like not to increase the length of the cycle. So each such vertex adds 1 to the length of some arc. So indeed we have a bound at least to t plus s on the length of the cycle. Any questions so far? Is it clear? Okay, and then I guess I'm telling simple things. So, all right. And to understand that this is not possible unless P is really large, we consider 2 cases, whether they have many common neighbors or they have not many common neighbors. So assume that they have at least delta minus 1 common neighbors. Then you see that T is greater than S. Then this bound is greater than 3 multiplied by S. And of course, this is at least 3 delta minus 3. And we assume that it is much greater than 2 delta plus P, because we have an addition of delta minus 3. Okay. So we should have that S is less than delta minus 1, or we can increase the length of the cycle. Yeah. So rewrite this in the form 2 over multiplied by sum of the neighbors minus the number of common neighbors. This is just inclusion-exclusion principle. Okay, and of course we know that U should have at least delta minus 1 neighbors on the cycle, because it just have 1 neighbor outside the cycle. And the same holds for V. So we obtain that there should be at least 4 delta minus 1 minus delta minus 1 cycle, or we can increase its length because we have some short arc. Okay, and this is, of course, is at least 3 delta minus 3, and this is greater than 2 delta plus P. Okay, so far we have shown that if we have an edge outside the cycle, we can increase its length unless P is really, really big. It is at least delta minus 3. Okay. So we can exclude the case of edge, because with the use of an edge, we can increase the length of the cycle. And this can be done, of course, in polynomial time. So we now may have isolated vertices, separable components, and 2 connected components. Okay. let us focus on two connected components. And we will see that they provide very nice structure of our graph. Okay, take two vertices of with the most number of neighbors in C. Okay, if H1, so the vertex with the most number of neighbors, has at least n1 neighbors on the cycle, then we know that the minimum degree of the two connected components is at least delta of G minus n1. Okay, and by Erdős-Galai theorem, we know that this bound on the degree yields a long path between H1 and H2, because we have an ST path of length at least delta. Okay, so consider some neighbors of these vertices. Again, use the trick that we used with edge. Consider the total set of neighbors and the set of common neighbors. Now we have a bound of 2t, or we can just increase the length of the cycle just by taking H1 or H2, for example. So we cannot have consecutive vertices of t on the cycle where we can increase the length. And now the common neighbors of H1 and H2, they add an arc of length at least delta minus n1 plus 2, because if we follow this long path, we follow this path, we would increase the length of the cycle if this arc is short. So the common neighbor of H1 and H2 should add very much to the length of this arc, unless we can increase the length of the cycle. Okay, and if we continue the arithmetics, we would obtain that n1 should be less than delta over 2. Okay, I won't get into this arithmetics because there are at least 3 cases of what can happen, but we would obtain that H1 has not so many neighbors on the cycle, or we can increase the length of the cycle. Okay, so we now have that n1 is less than delta over 2. And assume now that we have a matching between the vertices of H and vertices of C of size at least 3. So we look at the matching like this. We can always ensure that this matching includes H1, but for H2 and H3, we cannot be sure what vertices these are. But we can always ensure that H1 is contained in this matching. Okay. All right. So this matching, it produces 3 arcs on the cycle. This, and this. We know that the degree of this graph is at least delta of G minus n1. So each of these arcs should have length at least delta minus n1 plus 2. Yeah, because we have a path between H1 and H3 of this length, H3 and H2, and H1 and H2. Right. So we should have at least 3 arcs of length at least delta minus n1 plus 2. Great. And now, because H1 has at least n1 neighbors on the cycle, these neighbors cannot be consecutive. So we have that at least n1 arcs on the cycle should be of length at least 2. So we have that the length of the cycle, unless we can increase its length, should be at least 2n1 plus 3 over this minimum degree of the 2 connected graph, because these n1 arcs can coincide with these arcs. But you see that I just took these 3 arcs from this. So I just additionally, apart from these n1 arcs, just added delta minus n1. And as soon as and 1 is less than delta over 2, we obtain that this number is at least 2.5 of delta. So we have that cycle should be long. So we can be sure that a matching between H and C is of size exactly 2. And you can know that it cannot be less than 2 because the graph is too connected. Okay. And since this matching size is really small, we can be sure that the minimum degree of H is very big. So it is at least delta minus some constant. This requires some discussion, but this is some technicality that I wouldn't talk about. So we have automatically that if the matching size between H and C is exactly 2, we can say that inside H, we always have long paths. These paths are of length at least delta of the initial graph. So if we just draw these neighbors of H1 and H2, we have that the long arcs that go between them should be of length at least delta, or we can increase the length of the cycle. So we have that this component, it is connected to the cycle in the following manner. We have two opposite small paths on the cycle, small because the length of the cycle is not very big comparing to 2 delta. So we have these two parts, and these two connected components can be connected only to these two parts. And I would like to claim that each two connected component outside the cycle is connected to the same opposite small path. Okay, assume that this is not true. So we have some two connected component, and it is connected to some other vertices not on these two parts. Of course, these two arcs should be at least delta. And then I would like to say that I can find a really long cycle if this situation happens, because I can follow this cycle, and then I take 1/2 of my cycle C, or I take another cycle, and I take the complement of the cycle. So either the first green cycle or the second green cycle provides us with additional half of the cycle C. So we take this long red paths, and we take at least half of the cycle C. So we obtain a path of length at least 2.5 of delta. So this is not really possible, this situation. So each two connected graph should be connected in this way. So in fact, we can take two small paths and two connected components would be connected only to these small paths. I should note that this already goes beyond the log's proof, so log do not consider that we need a cycle much longer than 2 delta. Okay, so we have the two connected components are connected in this way, and assume that we have at the same time a two connected component outside the cycle and an isolated vertex outside the cycle. So it looks like this. Of course, an isolated vertex has many neighbors on the cycle. So if we have an isolated vertex, we can always find this picture, so that we have two neighbors that are situated between these blue arcs, so they are on the opposite arcs. Then we can again do the trick. We can find this long cycle or this long cycle. Okay. So in fact, we get that isolated vertices and two connected components are not possible at the same time. And I do not consider here separable components because their consideration is much more technical than for two connected components. But for separable components, we can also prove that they are connected to the small opposite path on the cycle. Yeah. So what can we say? We proved that we cannot have at the same time an isolated vertex and two connected components. So by following the steps of enlargement of a cycle, we obtain that we can have either isolated vertices outside the graph or large two connected or separable components outside the graph, but not at the same time. And for isolated vertices, in a warm-up example that we considered, we know that isolated vertices have many neighbors on our cycle, because the length of the cycle is not much greater than 2 delta. We have that there are many one-on-one neighbors of isolated vertices. I mean, there are many situations where you have isolated vertex and such a vertex, and it is, of course, one-on-one neighbor. And we already know that one-on-one neighbors, they should be independent, or we can increase the length of the cycle. So when we obtain isolated vertices, but not two connected or separable components outside the cycle, then we obtain a small vertex cover of the graph, because we have many one-on-one vertices inside the cycle. And for the second case, when we have two connected or separable components, we have a really good structure in our cycle. Well, it's not really clear why it is good. We will show it a bit later, but we have it, okay, like this. I'm sorry, I will close now any comments. Okay, yeah, so isolated vertex provide us with vertex cover, and two connected and separable graph provide us with so-called Dirac decomposition. We will define what is a Dirac decomposition a bit later. But now let me formulate the main structural lemma that you can see in the title of this slide. Let me erase the comments. So what we obtain from the ideas of Locke, from his proof, modified with some new ideas, we obtain that if we are given a two connected graph in a cycle of length 2 delta plus small number, we can in polynomial time either find a longer cycle or a small vertex cover, where, of course, vertex cover should be at least delta plus some small parameter, or a Dirac decomposition of our graph. Okay, and this is the main structural lemma in our work. This is what we rely on to solve long Dirac cycle. And we will see how it is structured in our paper. Okay, any questions so far? Any question concerning the sketch of the proof of the main structural lemma? Okay. So, and what we should take a look at now is the problem graph of our work. So we see here that the central problem of the work is the long Dirac cycle. And to solve it, we would like to solve some other problems that handle different cases arising from the main structural lemma. You can see that one of the cases here is the Dirac decomposition. And to deal with it, we introduce a very natural problem called longest T cycle. I will define it in the next slide. And the problem that we already defined is longer Dorgala ST path is a friend of long Dirac cycle. And the other case, principally the other case, is the case of small vertex cover. And then we should introduce another problem. And this problem we solve with, again, modification of ideas that were used by Janssen, Kozma, and Nederlof. They took ideas of Hagquist that were defined much earlier. Yeah, I will talk a little bit about it. So for now, let me focus on the left part of it. And let me also say, what is this problem? This problem is actually a problem that was formulated by Janssen, Kozma, and Nederlof in their work, where they asked, what if we have k vertices with degree less than n over 2 minus k? And this problem we need, in fact, to deal with bad vertices. Because when we have bad vertices, we cannot, so we have bad vertices outside the cycle, and we cannot actually embed them into cycle because they have no many neighbors inside the cycle. So this problem is separate, but it uses the ideas of small vertex cover. It uses this as a black box because in one of the cases we obtain a small vertex cover when we try to embed a bad vertex inside the Hamiltonian cycle. Okay, so let me just briefly define two problems that will go beyond the scope of this talk. This is an almost Hamiltonian Dirac cycle and the longest T cycle. About the first I already told. About the second, so okay, we have, yes, of course, yeah. So we are just given two vertices S and T, and we would like to find a simple cycle that consists of at least k edges and passes through simultaneously S and T. And this problem we solve not for two connected graphs, but for general graphs using color coding and some structural lemmas that describe how, what type of cycle should we look for. Okay, any questions so far? I see some dots on the board, maybe it's for drawing my attention. Okay. So again, we take a look at the problem graph and we focus on the left part. Precisely, we focus on Dirac decomposition. Okay, so Dirac decomposition looks like this. Gray vertices here are bad vertices. And we won't pay much attention to them. They are not really relevant here. The main property of Dirac decomposition is that we have two small paths. And when we delete this path, we obtain large components because their minimum degree is large. And a matching between the path and this component should be of size 2. In fact, we have a matching of size 1 between P1 and the component and a matching of size 1 between P2 and the component. And this is useful for the following reason. This allows us to restrict the cycle we look for, because when we have such a small matching, so when we start in P1 and go inside the component, then we cannot construct a cycle like this. Go here, go outside, then again go here, go outside. Because of the matching size, there is a bottleneck that doesn't allow us to enter the component and exit without leaving here. Also, it doesn't allow us to enter and leave more than once. So the only way that we can go through this component is to go through it completely from P1 and exit from P2. Okay, this is the main property of Dirac decomposition. Yeah, and here the main object here is a Dirac component. For two connected graphs, Dirac components are just these components. And for separable graphs, Dirac components are their leaf blocks because they are two connected. And of course, the main property of Dirac components is that they are of very large degree, almost delta. So in each Dirac component, we have a really long path between any pair of vertices. So when we enter such a component, we can take a really long path inside it and then leave it and never enter again. Okay. So, okay, we have these components are two connected. This is separable. This consists of only bad vertices. And these are Dirac components. And the main lemma here is that if there is a cycle of length at least 2 delta plus k, then there is a cycle of length at least 2 delta plus k that goes through two distinct Dirac components. This is a very main lemma that its proof is very involved. And if I tried to prove it here, well, I would require 40 minutes or so, I guess. So what lemma says that we can just fix two distinct Dirac components, fix two long paths inside them, and then just look for a way to connect them using the edges and vertices outside. So we have that these green paths are of length at least delta, and we would like to find these orange paths that connect these green paths. And we require just k or so of these orange paths, because these green paths are already long, and we look for at least 2 delta plus k. So we do not require these orange paths to be very long. And to find green paths, we use the longer Dirac ST path problem, because we have a two connected component with large degree. And for finding orange paths, we use ST cycle, because you can see the reduction. You just connect S with endpoints of one path and T with endpoints of the other path, and look for a cycle of length at least k. So since these problems are both FPT, we obtain an FPT algorithm finding a long cycle in a Dirac decomposition. Any questions so far? This allows us to handle Dirac decompositions using ST cycle problem and longer Dirac ST path problem. Okay. Now I focus on how we solve longer Dirac ST path problem. Actually, we solve it with the same ideas of enlargement of a path instead of a cycle. So we start with an arbitrary ST path and try to enlarge it using the ideas discussed earlier. And now isolated vertices are not possible outside the path. So we again obtain some decomposition that is pretty much relevant to the Dirac decomposition. And this decomposition we call Dirac. You see the connection. So this is related to Dirac theorem. So it is a Dirac decomposition. And for Dirac is the same. And here, the problem is easier in some sense, because if we look for an ST path, so endpoints of this path are S and T, we can now go like this. We know that a long path goes through any Erdős-Galai component. And here we can just fix such a path. And again, using the ST cycle, find two disjoint paths that connect S and T with endpoints of this path. Yeah. Again, we use longest T cycle to connect it. But the main difficulty here, it is a technical difficulty that we should apply the Erdős-Galai algorithm recursively. So we should apply the same decomposition inside this R1 component. So we go there and try to enlarge the path, and there we obtain either a long path, and then we connect it using ST cycle, or we again obtain a decomposition and again solve it recursively. And this recursion requires a good induction hypothesis. Okay, this is quite technical, but it goes pretty much as I described. Okay, let me clear all my drawings. Okay, and the last problem I want to focus on, just very briefly, because I have no time, is the long Dirac cycle when we have a very small vertex cover. So what is the problem about? So we have a very small vertex cover of size delta plus small number. Put I to be an independent set, and we know that any long cycle contains at least delta vertices of S, because we have a guarantee of 2 delta. And we know that the length of the cycle cannot be more than 2 times the number of the vertex cover vertices inside this cycle. And now the idea here that since each vertex in I has at least delta minus p neighbors in the cycle, we can force very many of them to be in the cycle. So if you consider this blue vertex, it is from independent set, we can insert it in the cycle. Then we have another vertex, we can also insert it in the cycle. Another vertex, we see that this is not allowed, but here we have a place for it. And since they have many neighbors, we can put very many of them in the cycle. Okay, so we forced a really big subset to be in the cycle. So we have already delta plus delta minus 3p. So we now need to take some number, say at least 6p into the cycle. Since X is very large, then at most 2p vertices in S have less than 2p neighbors in X. Let their set be Z. And then using the Bondi-Quatal lemma, it says about the closure of Hamiltonian graphs when 2 vertices have the total degree at least n, you can connect them by an edge, and this doesn't change the Hamiltonicity of the graph. Then we can use the sets S, X, and Z to form some path cover. And if we find such a path cover, then we can merge this path into a cycle. Unfortunately, I have no time to go into the details of this, but if you have any question about it, you can ask. Okay, and these are ideas, I mean, about the path cover that with the Bondi-Quatal lemma is constructed into a cycle. These are ideas of Hagvist that were used then by Janssen, Kozma, and Nederlof. They were modified to obtain an FPT algorithm. And then we also generalized these ideas to obtain more robust path cover when restrictions are more strong. Okay, this is what I can say about the long Dirac cycle with the vertex cover. So we considered at least 4 points of the problem graph. And now I want to summarize and discuss some open questions. So what we have shown, well, we have shown that a cycle of length at least 2 delta, where delta can be considered minus some number of vertices, plus some parameter. In a two-connected graph, we can found it in single exponential time, depending on the parameter k plus the size of b. And to the exponential time hypothesis, this dependence is optimal. You cannot get a small o of k plus b. You cannot obtain exponential algorithm, a sub-exponential algorithm, but I am not sure about the dependence in the size of b. Maybe you can make it less. I'm not sure. It needs some checks. Okay. And this problem nicely generalizes several other arising problems, such as long Dirac path, longer Dirichlet path. You can see that we can reduce a longer Dirichlet path to long Dirac cycle, but we use longer Dirichlet paths to solve long Dirac cycle. Yes. And the same for almost Hamiltonian, this should be almost Hamiltonian cycle without Dirac. Okay, so this is an open question. So this was an open question posed by Janssen, Kozma, and Nederloh. Okay. And well, I want to conclude with some, okay. We also solve a problem of longest cycle, which can be of independent interest. I would say that it is pretty natural problem solved in single exponential time in optimal time. And an open question is, can we extend these results or maybe discuss some other constructions, invent some other constructions, and consider other above guarantee versions for finding passes or cycles? For example, we have no idea how to solve the average degree guarantee. So one of the theorems says that we always have a cycle of length at least average degree. Can we do better than that? Also, in k-connected graphs for k more than 1 or 2, we can force this cycle to go through specified set of vertices of size less than k. So can we find cycles of length 2 delta plus k going through specified set of vertices, if we are given that the graph is connected enough? And also, there are some analogs of Dirac's theorem for directed graphs. Can we say something about algorithm for them? Well, I would say that we can find many other theorems and formulate the problem for them. Just these are the problems from extremal graph theory. Okay, so thank you for your attention. Any questions are welcome.
Thank you for the talk, Danil. And yes, we are open for questions. If you have any questions, please unmute and ask. Or if you prefer, you can type in the chat. All right. I suppose there are no questions.
Yeah.
So, all right. Thank you once again for the talk. It was great to have you here.
Yeah.
And thanks to the audience for being around. We conclude our session for today and see you all next week. Thank you. Bye.
Thank you very much. Bye.